Okay, in this last ketone aldehyde video, what we're going to look at is spectroscopy, and then we're going to look at one additional, more advanced problem here. Okay, so first let's look at the infrared spectroscopy of carbonyl groups. And what I say here, I'm using ketones and aldehydes as an example, but what we're looking at goes for esters, carboxylic acids, amides as well. Those trends that we talk about here are going to be going on for those compounds as well. Okay, so remember in the beginning of the ketone section, we looked at how this resonance interaction here could explain a lot about the relative reactivity of carbonyl group compounds. It can also explain a lot about the infrared spectroscopy. What we need to remember here is this important equation from physics. Right? Where what we can see is there's direct proportional relationship between energy and frequency. Okay, so in infrared spectroscopy, remember we're looking at the frequency of a bond stretch in most of the bands that we look at. Okay, all right. So when you consider these two resonance structures, the one on the left is a double bond. It's going to be stronger and it's going to be harder to stretch. The one on the right is a single bond, and it's going to be a little bit easier to stretch because it's a single bond instead of a double bond. Okay? So if we destabilize the resonance structure on the right, the C double bond O becomes stronger and it becomes harder to stretch, and it stretches at a higher frequency. Okay, we know several things that would make this positive charge here more prominent. Okay, so if we put an electron donating group in the vicinity, that's going to stabilize the positive charge, and that's going to make the single bond resonance form more prominent. Okay, if we conjugate, if R1 is a alkene or a benzene ring, then this becomes a benzylic or an allylic carbocation, and that's also imparts some degree of stabilization to that alternative resonance form, right? Okay, all right, so we're going to see that effect as well. All right, so let's look at some of these down here. So let's look at these three here. Okay. The only difference here is that we have the one on the left, that's benzaldehyde. We're going to use that as our base value. It's 1703 wave numbers for the carbonyl stretching frequency. Okay, the nitro, remember, is an electron withdrawing group. And as predicted, we see the infrared stretching frequency become a slightly higher number at about 1710 wave numbers. Okay? All right, now we put an electron donating group. This is this diethylamino group, and what we see is a lower stretching frequency. It's down there at 1682. We're stabilizing the single bond resonance form. Okay, over here we have some other interesting things. If we take cyclohexanone at 1717, but we add this double bond here, conjugating the system, and here we see that the stretching frequency has dropped quite a lot, by almost 30, actually by 35 wave numbers. Okay, so conjugation results in a lowering of the stretching frequency as well. Okay, the effect is more or less additive. You see, in this case, we have two benzene rings here, and the stretching frequency is all the way down at 1666 wave numbers. Okay, let's look at NMR spectroscopy. Right, if ever you're given an unknown compound and it's an aldehyde, what you should do is you should find your instructor and say thank you. Okay, because the aldehyde hydrogen, shown here, is one of the most unique NMR absorptions that we have in organic chemistry. This proton comes 9 to 10 parts per million, oftentimes a little bit higher. Let's say 9 to 10 and a half parts per million would probably be a better description of the range for that absorption. Okay, if we look at the hydrogens at the alpha position, we see that their chemical shift is a little bit higher too, not quite as high as if there's a oxygen or a chlorine or something directly attached, but this alpha position of aldehydes and ketones and esters and carboxylic acids as well, it comes about 2 to 3 parts per million. There's no real difference here between an aldehyde and a ketone. Okay, of the C13 NMR, we have, this is our unique feature here, the carbonyl group, and when it's a ketone or aldehyde, it comes usually 190 to 220 parts per million. Okay. When it's an ester or carboxylic acid or acid chloride or amide, it's actually much lower. It's 160 to 185. So here we have, if you look at the C13 NMR spectrum, I'll put this number out here, 187. Okay. Anything higher, this ketone or aldehyde. Anything lower is a ester, carboxylic acid, amide. Just something that has a heteroatom directly attached to the carbonyl group, like an oxygen or a nitrogen. Okay, all right. So if the chemical shift of your carbonyl group is like somewhere between 185 and 190 or so, I guess we would call it an unreliable gray area, but usually you can tell the difference between the ketone aldehyde absorption and the all other types of carbonyl group absorptions by this dividing line here, right in the middle between 185 and 190. Okay? All right, so let's look at some examples of some spectra here. Okay, let me just say one other thing here. When we discuss NMR, we've kind of focused on things that follow the n+1 rule, but the aldehyde is actually going to introduce a situation where the n+1 rule is not followed, and this is because this 3-bond coupling here isn't typically very large. It's typically less than half of what your normal 3-bond coupling is. So oftentimes when you have an aldehyde, you won't see the n+1 rule followed. Okay, so here's n-butyraldehyde, or 1-butanal, or sorry, actually butanal. We don't even use the number here. All right, if we don't really expand the spectrum, we see something that looks like it follows the n+1 rule here. This methyl group looks, there's a triplet. That's a sextet. This looks kind of like a triplet, but you see this triplet here is a little bit thicker than that triplet there. So we're going to blow it up and see what it really looks like. The aldehyde peak here at 9.75 looks like a singlet at this magnification level, but let's blow it up. If you blow it up, you can see here that this is actually a triplet with a small coupling constant. Okay, and what you see here is that this triplet I was talking about before really isn't a triplet. It's called a triplet of doublets. And this is because when we look at this proton here, it has a typical degree of coupling there, but a much smaller coupling between here, okay? So this results in a situation where we're not going to follow the n+1 rule perfectly. Okay, let's look at a compound that has both a ketone and an ester in it. And right here you see two carbonyl groups. And this one at the high chemical shift, this is the ketone. And this is the ester. Okay? All right. So you can see this dividing line I put here, like right around 187. Yeah, this molecule obviously quite simple. It only has two carbonyl groups in it. But what we're going to see as we look at more and more examples, we're going to see that we can tell the difference between ketones and aldehydes and other types of carbonyl groups by the C13 chemical shift of the carbonyl group. All right, here's an unknown. Again, you should try and solve this on your own and then restart the video after you solved it just to see if you got it correct or not. All right, so let's look at how we would approach this problem. All right, so like unknown problems, what we should do is calculate our degrees of unsaturation first. There's our formula, C11H14O2. This has okay, so there's our degrees of unsaturation are 11. Okay, that's where I'm messing up. 22 and 2 is 24, minus 14 is 10, divided by 2, so there's 5 rings plus multiple bonds. Okay, in the spectroscopy chapter we said if you have an unsaturation count of 4 or higher, you should instantly suspect that you have a benzene ring in your molecule, and it looks like we do. Okay, so there's our benzene ring. And our benzene ring, remember, has 4 degrees of unsaturation. We'll just say 3 double bonds plus 1 ring. Okay, this must mean that we have one more unsaturation, and we can see right away that it's a C double bond O. Okay, knowing that we're in the ketone chapter when we're doing this problem, it's probably a giveaway that it's going to have a C double bond O in it, but let's just make sure of that. All right, so we have a C double bond O in this molecule. All right, now what we can see here is that it's at 208, so therefore it's a ketone or aldehyde. And we can rule out the aldehyde because there's no peak above 7.5 ppm in this molecule. And the aldehyde hydrogen would have to come at 9 to 10. All right. So what's in this molecule? It's what we see here is that the integration values add up to be 4. So this means it's a di-substituted aromatic. Okay, the only coupling we see outside of the benzene ring region are these two. And these are both 2 hydrogens, and they're triplets. So this means that we have in our chain here some situation where we have 2 CH2 groups beside of each other, and our X and Y groups here have to be chosen, so there's no further coupling. The only coupling is of those CH2 groups to each other. All right, this is an OCH3 group. Okay, because of its chemical shift and the fact that we have oxygen in the formula, that's the most reasonable case for this. This is also a methyl group, and its chemical shift at 2.2 suggests that it's either that type of arrangement. Okay, our aromatic ring, it's di-substituted, but we can sort of see that we have two different protons. So the question, ortho, meta, para, it's got to be para due to the symmetry present, okay? All right, so there's a lot of evidence of symmetry, right? There's 11 carbons, but when we count carbons in the C13 NMR, 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only 9, so there's got to be some symmetry in this molecule. All right, so it's a para-substituted aromatic. It's got two CH2 groups adjacent to each other on its side chain. It's got an OCH3 and a CH3. When we assemble these, this is the structure, only structure that fits. Back in the spectroscopy chapter, I would have given full credit for this alternative structure right here, but I'm not going to give full credit anymore because now we can see some reason why that structure does not fit, right? And that's because this carbonyl group should be less than about 185 or so, and we're seeing that it comes at 208, so we can rule out an ester as being the structure here, okay? All right, so now that we know a little bit more about carbonyl groups, we can definitely say of these two structures that it has to be the top one. Okay, this last one here is a synthesis problem. There's one more slide after this where we're going to look at a phenomenon that we're going to come across in the future. How do we synthesize that compound? And we're going to say in our directions you can use any alkyl halide, Grignard reagent, or Vinegar reagent as your source for extra carbons, and you should avoid steps that produce isomeric byproducts, okay? This is often a cue in your problem that you want to use the Vinegar reaction instead of relying on Zaitsev's rule to deliver your double bond to the right place, as you see here in the product. Okay, so our last step should be the Vinegar reaction. Okay, let's also look at how many carbons we have in the starting material versus product. Okay, so there's the carbons where they end up in the product. So what do we have to add? We have to add an isopropyl group, and we have to add this group. Okay, all right. We're using either Grignards or Vinegar reagents. We can't really add Grignards directly to carbonyl groups and get ketones directly. We'll might look at some of that in the next or a couple of chapters up, but we haven't had a method yet that does that. So this is really going to have to come from oxidizing the secondary alcohol to the ketone. And since the alcohol is secondary, we can use just about any oxidizing agent to successfully do that. I just said chromium-6. We could use pyridinium chlorochromate or H2CrO4. We could use the Swern oxidation as well with DMSO and triethylamine. Okay. All right, so now that we have this, we remember that when you make alcohols, you can make the bond adjacent to the OH group through the Grignard reaction. So that bond there could easily be constructed through a Grignard reaction. So we would treat that aldehyde with isopropyl Grignard and then do the aqueous workup, and that would give us that. All right, and to convert the alcohol to the aldehyde, all we need is PCC. And this, we have to have PCC or the Swern oxidation because we would be concerned about over-oxidation to the carboxylic acid. All right. In the last step, there is another way you could get an alkene in there. That's to add the Grignard and then do an elimination, but this would not be quite as good a method because we would make too many isomeric compounds, right? And another problem here is if we look at Zaitsev's rule, of course, the one we want isn't even the major compound. That's predicted to be the major because it's a tetrasubstituted alkene. Okay, let's see. This is the last slide here, and this is an issue that we're going to visit in the carbohydrate chapter. But remember a few slides ago, or a few videos ago, we said that hemiacetals usually aren't stable. But there is one class of hemiacetal that is stable, and that is when we form moderately stable if we produce a 5 or a 6-membered ring. Okay, so carbohydrates like glucose here have one aldehyde group or one ketone group in them and lots of hydroxy groups. So these can form a stable hemiacetal by taking the aldehyde at carbon 5. Here's the IUPAC numbering system. So I'm going to add that OH group to the carbonyl group. This is going to make a hemiacetal, which recognize that here it was sp2. Now it's sp3 and chiral. And when we draw it in the chair form, okay, it looks a lot prettier. And you can see that you have these nice chair forms of the carbohydrate system. This is not until very late in the class that we're going to talk about this issue, but just remember that I always was very carefully to use the word usually when I said that hemiacetals were not stable. And this is why we're going to find that later on we do have a major exception to that rule. So this is the last of the videos in the ketone and aldehyde section.